Hello everyone, this is Alfio Sando. Today I'm going to continue CUDA programming series. I'm going to talk about thread cooperation and how to use this technology to optimize our CUDA program. I will use a vector dot product calculation as example to showcase how to use this technology. If you like these videos, you can support me by subscribing my channel or click like of the video. You can find the code of the example and all of my video list in the description below. In last videos, I briefly talked about kernel function. However, I haven't touched the parameter inside the forward arrow and the backward arrows. There's a couple of parameters can be defined. Then first two basically is very important. The first one is number of blocks, and the second one is number of thread. When we define kernel function, the CUDA will mapping our all requirements in a grid, and a grid can have multiple blocks, and a block can have a multiple thread. By given the total number of blocks and thread we want to have in a grid, the compilers will copy all those functions into each thread and running those functions parallelly in each thread. Then that's how we use the block and thread in CUDA programming. So in today's examples, I'm going to show how we calculate two vectors dot product. By mathematics, the dot product is the multiplication of each element of tensors or vectors. Then basically we sum all the partial multiplication result together and into a scalar value. As in showing these pictures, one straightforward way we can do that is to declare two arrays for A and B vector for each element. Then for each element, we do multiplications operations. We save the partial result into array. Then finally, we sum all the elements together into a scalar to get our result. Let's take a look how we implement these algorithms into CUDA. As previously examples, we allocate A, B, C in the CPU side and device A, B, C in the GPU side. Then we initialize our A vector and B vector. So this is an important one, how we call our kernel function. Please ignore the name of the function because I believe this is not incorrect for these examples. Here we define we want to use 128 block and 128 thread. In the kernel functions, we need to know which thread index we currently running. So basically we can do that by obtain the current thread index plus the current block index and get how many threads in each block. For examples, here if we thread index is 1 and the block index is 1, then block dimension here, if we use 5 thread in a block, then it will be 4, and 4 plus 1 is 5. So our final thread index. So here we find the correct index and access the elements in A and B vector. Then we multiply them together, store in a C array and output. Here we copy the memory from device to host to C. Then we sum them all the elements together in an array to get a result. Of course, we still can improve these programmings. One pain point we have is we need to always have the n dimension allocate for C array. As you maybe all know that copy from the data between two devices is very costly. So that way we can reduce the size of the C, but still achieve the same result. So here we can use thread cooperations concept. An improvement we can do is that we completely redefine the kernel function. Here we use a shell memory. So once we have the shell keywords defined, so these variables can be accessed by all the threads in a block. So here we declare this array size by threads per block. So each thread in this block have a slot. Again, we obtain the final index, and the cache index for this implementation is just the thread itself. We will store elements multiplication into the cache slots. Then we call sync threads. This is another important concept. Imagine that all the kernel functions are parallel running, but there's no guarantees they're all running the same speed. For example, the first index, when it's running at this line, but the fifth thread maybe is already at this step. So the sync threads is help us to let all the threads wait for the slowest threads until they all reach in the same point here. Why we do that is because we need to use all the data in the cache. Now, next step is basically we're trying to reduce all the elements in C to a same slot. So basically it's kind of reduced concept, and if you happen to see the LeetCode merge K list problems, it's also a kind of divide and conquer problems. Then the algorithm is shown as right side. We will do multiple iteration. Then for each iterations, we have an array to store all the elements multiplication result. Then for this array, currently we have 8 slots. We're trying to reduce to save all the data in 4 slots. What we do is we add in the data between 0 index and the 5th index together, and the first index to the 5th index together to generate the partial sum result, then stored in the first half of array. Then for the second iterations, of course, our length from 4 reduced to 2, then to 1 eventually. Then this is what is while loop is doing. And here, please be noticed, we also need to call sync thread again because we need to use all the rest of the cache index in the next iteration until we have 1. In the end, we successfully to save all the data in the first index of the array. So we will save them into C and sending out. In main functions, we still have A and B and divide by n dimension. The really difference is that we can only define partial C, only use blocks per grid as cost. After calling the kernel functions, we copy data from GPU to the CPU. Here we need to do a final round of sum because our partial C still is an array. So after these operations, we will have a single scalar values. Then we print this out. You can compare with this numerical value with the previous version. You can find they are identical. If you happen to know how to profiling CUDA programs, please do so. I believe this should be giving us some boost of the running speed or maybe the memory cost. Okay, so that's all the topics I want to cover today. Hope you like it, and I'll see you in the next video.